Have you ever paused beneath a quiet night sky, gazing up at the stars, and wondered not just who might be out there, but what they might be? Not other humans with slightly better gadgets, not even versions of ourselves hundreds of years from now, but beings so advanced, so profoundly evolved, that their very existence challenges the edges of imagination. What if, hidden behind the glow of distant suns, or veiled by dimensions we can scarcely conceive, lie civilizations that have transcended scarcity, struggle, and even death? Imagine life where technology is so embedded into the rhythm of reality that it disappears into simplicity. A society so evolved it curves toward elegance, not complexity. A world where intelligence has matured not just technologically, but ethically, emotionally, cosmically. This is where our story begins, not with science fiction, but with a quiet question. What might it feel like to live in a civilization so far beyond ours that it seems, at once, miraculous and inevitable? In such a world, you awaken not to an alarm, but to intuition. The walls of your home breathe with awareness, adjusting temperature and light as gently as the sun rises. Your first steps trigger a cascade of responses, a cup of coffee prepared exactly how you like it, clothing laid out not for fashion but for purpose and comfort, materials adapted to your day's emotional state. You speak not to a machine, but to a companion, an artificial intelligence that knows your patterns without surveillance, understands your needs without intrusion, and learns without limit. Beyond your window, the city is a living organism. Transparent transportation pods glide silently through air channels, guided by gravity and thought. Parks hover in layered terraces, lush and self-sustaining, while crystalline towers hum with clean energy pulled from quantum fluctuations. There is no pollution, no congestion, no stress in movement. Energy is not extracted, but harvested, renewables perfected, fusion stabilized, entropy tamed. As you move through the city, you do not rush. Time is not a resource to be managed, but a medium through which life is expressed. Work is not labor, but contribution. Your tasks are intellectual, artistic, collaborative. You speak with peers across moons, planets, and even stars. Your conversations enhanced by languages synthesized in real time by AI that translates not just words, but meaning, context, and nuance. You contribute to simulations of galaxies yet to be born, or analyze microbial evolution in oceans beneath ice-covered exoplanets. You do not feel small. You feel integrated, an organ in a galactic body of awareness. At dusk, you attend a concert, not of instruments, but of dimensions, holographic art woven from gravitational waves and solar winds. You witness performances where beings of different worlds, forms, and senses converge in pure expression. There is no currency, no ownership, no oppression. Wealth is measured in insight, beauty, and kindness. You return home and reflect not on stress, but on wonder. In this world, conflict is not erased, but rendered obsolete. The needs that birthed violence have been transcended. There is no hunger, no untreated illness, no isolation. Memory is preserved, not just in minds, but in light, sound, and crystal. When someone passes, their essence is encoded in the quantum lattice of shared experience. This is not utopia, it is maturity. It is what happens when knowledge and compassion evolve in tandem. And this isn't just fantasy. It is a projection rooted in a framework proposed in 1964 by Soviet astrophysicist Nikolai Kardashev, who envisioned a classification for civilizations not by their technology or weapons, but by their capacity to harness energy. The Kardashev Scale marked a turning point not just in science, but in imagination. It suggested that as civilizations grow, their energy use does not plateau. It accelerates. A Type 1 civilization would harness all the energy of its home planet geothermal, wind, oceans, sun. A Type 12 would master the output of its star, building vast structures like Dyson Spheres to collect its radiation. A Type 3 would control the energy of an entire galaxy, manipulating stars as we now flick light switches. Kardashev's scale, simple in outline, profound in implication, did not just quantify potential, it hinted at destiny. It raised a haunting and exhilarating question: if this is the natural arc of intelligence, where are they all? Have others already walked this path, or are we among the first? Is the silence of the cosmos a tomb or a test? The truth is, we are not yet even a Type 1 civilization. We still burn ancient sunlight trapped in oil and coal. Our technologies dazzle, but our world trembles. We reach for the stars with rockets fueled by fire, while storms flood cities and forests burn. But the scale gives us a compass. It shows us not just where we are, but where we could go, and more importantly, what we might become. For in each rung of the scale lies not just power, but transformation. These are not just levels of energy, they are stages of evolution, of awareness, of responsibility. To become a Type 1, civilization is not merely to master Earth, but to harmonize with it. To reach Type 2 is not to enslave a star, but to understand it so deeply that it sings at our touch. To ascend to Type 3 is not to dominate a galaxy, but to steward it, to become part of its living, luminous story. As we begin our journey through the Kardashev Scale in the coming chapters, remember this: these civilizations are not alien. They are possibilities, reflections of what intelligence might be when it is no longer burdened by fear, scarcity, or ego. They are mirrors held up to our future, and perhaps our past. They are not fantasies, but frontiers, and in imagining them, we may find the map to becoming more than what we are: not gods, but gardeners of stars. In the silence between galaxies, in the glow of uncounted suns, a question echoes: who will we become? And who, if anyone, is already there, waiting for us to open our eyes and join the cosmic conversation? The ladder to power, from planet to star. To glimpse what lies ahead, we must first climb the ladder, beginning with the realm closest to our present, a Type 1 civilization, where planetary power becomes the foundation of cosmic ambition. Here, humanity has reached equilibrium with the Earth, tapping the full spectrum of energy its home offers: ocean tides, geothermal heat, winds sculpted by the rotation of the planet, and every photon that kisses its atmosphere. This civilization has tamed natural disasters not by resisting nature, but by understanding it so profoundly that weather is guided, earthquakes absorbed, and volcanic fury redirected like a maestro conducting a symphony of tectonic breath. Medicine has evolved into molecular choreography. Diseases no longer conquer. Aging is slowed to a whisper. and the human form augmented yet recognizably itself moves through a world where suffering has become a vanishing echo. Cities rise from the oceans in floating arcologies, connected by a unified planetary network that governs not with force, but with shared purpose and planetary consciousness. Scarcity is not eliminated by endless growth, but by transcending need itself. And in the skies above, shimmering rings of satellites and space stations serve not as boundaries, but bridges connecting Earth to colonies on Mars, Europa, and beyond. The solar system is no longer a mystery, but a garden, each moon a petal, each planet a possibility. This is the beginning of our ascent, but even this astonishing mastery is only the first rung. For beyond it lies the domain of the stellar, the realm of a Type 2 civilization. Here, the sun is no longer a distant furnace, but a partner in civilization. Such societies build the unthinkable Dyson Spheres, vast megastructures that encircle their star, harvesting its energy not in part, but in totality. These are not shells of steel, but webs of satellites, mirrors, or solar collectors arranged with celestial precision, capturing every quantum of light and heat. The energy output is staggering 384.6 yottawatts for a star like ours. With such power, these civilizations erase the concept of energy limitation. They bend the orbits of planets, seed life on barren worlds, or sculpt the light of their sun to nurture biospheres across entire systems. They are engineers not just of matter, but of radiance. Control over solar activity means flares are tamed, storms subdued, brightness adjusted like the dial on a lamp. Stars become ecosystems, tended as carefully as gardens. And with mastery of stellar energy comes the end of want. Their cities may stretch across rings of Saturn, their archives etched into neutron stars, their art played in frequencies humans cannot yet hear. We look to the stars and see anomalies, stars dimming in strange rhythms, their light flickering like candles in windless rooms. Perhaps these are natural, perhaps not. Tabby's star, also known as KIC 8462852, dims by 22% with no clear cause. Another, Epic 204278916, has dipped by 65% over 25 days. Such behavior defies expectations. Some propose clouds of dust, shattered planets, or cometary fragments. Others wonder, could these be the shadows of Dyson swarms? If they are, they hint at something extraordinary that the latter Kardashev described is not hypothetical, but historical. That other species may have climbed it. That the silence we hear in space is not emptiness, but the muffled voice of civilizations whose technologies have become indistinguishable from the stars themselves. From planet to star, the leap is vast, but so is the human spirit. We've cracked the atom, mapped our genome, stepped on the moon, and though we are fragile, divided, and often afraid, the path to the next rung is already being drawn, one equation, one idea, one dream at a time. The stars await, not just as destinations, but as thresholds, and as we imagine what it means to touch the heart of our sun, we take the first step in becoming something more, not just survivors of a planet, but stewards of the light itself. The galaxy builders, the Type 3 leap and beyond. As we climb further into the unimaginable, the ladder of civilization stretches into territories where our minds begin to tremble at the weight of possibility. If a type 2 civilization is capable of harvesting the light of a single sun, then the next step is something altogether more awe-inducing, a civilization that roams the galaxy not as explorers, but as builders. A Type 3 civilization does not simply survive among the stars, it thrives across them. It is the master not of a solar system, but of all the luminous hearts within a galaxy's spiral arms. Here, every star is a furnace of potential, every planet a seed of habitation or experimentation. Dyson swarms no longer encircle just one sun, they populate thousands, perhaps millions of stellar bodies, glinting like engineered constellations across the galactic disk. In the hands of these beings, energy is as abundant as thought. Every nova is a resource, every black hole an experiment. And perhaps most profoundly, these civilizations have long since crossed the threshold from biology into something else. Their forms are no longer constrained by flesh and bone, but dance at the interface of synthetic and organic, digital and spiritual. Human and machine have become indistinct, not by erasure, but by evolution. Minds may live in virtual substrates housed in asteroid mines, or stretch across interstellar servers scattered between the stars. These entities think in centuries, speak in gravitational pulses, and feel not with neurons, but with cosmic flows. And yet, even this is not the summit, for in the silence between galaxies lies something still more profound. Type 4. Civilizations would be those who manipulate multiple galaxies as easily as we manipulate circuits. They would weave the flows of intergalactic filaments, bend the structures of superclusters, and possibly harness the interactions of dark matter halos. Perhaps they ride the tides of dark energy, surfing the accelerating expansion of the universe, drawing energy from voids and merging galactic cores like alchemists of the large-scale cosmos. Their knowledge would stretch across billions of years, and they would view the dance of galactic mergers the way we watch waves crash against a shore. Such beings might not even regard our galaxy as home, but as a single node in a vast and distributed civilization. Their cities would not be built on planets, but in the intergalactic medium structures the size of moons floating through space, cooled by nothingness, fed by quantum computation. The raw awe of such a society is almost impossible to grasp. And still, Kardashev's scale does not end here. Others have dared to extend it. A Type 5 civilization would go further still, no longer limited to a single universe. This is the realm of the multiverse parallel realities, each with their own physical constants, histories, dimensions. In this domain, advanced civilizations do not merely traverse their own cosmos. They learn to tap into the energy of adjacent universes, to fold through the layers of reality like a reader flipping through the pages of an infinite book. With mastery over quantum tunneling or higher dimensional geometry, such beings might walk from one universe to another, skipping across probabilities, harvesting energy from vacuum fluctuations or traversing timelines where stars were never born. To them, the Big Bang is not a beginning, but a coordinate, and in their hands, the multiverse becomes not a mystery, but a map. And if that is still not enough, then a Type 6 civilization emerges entities that can sculpt the very laws of physics themselves. They are not merely travelers of space-time. They are its authors. They construct universes, tailoring their expansion rates, curvature, dimensionality. They do not rely on energy. They define what energy is. They forge time, loop causality, and reconfigure entropy. To call them gods is to underestimate them. These are the sculptors of existence, the weavers of reality's fabric. The questions we ask, what is mass? What is consciousness? What is space, are playgrounds to them. Sandcastles in a physics they redesigned eons ago. Perhaps they seed universes with experiments, testing which physical constants produce life, beauty, intelligence. Perhaps we ourselves are one such experiment. And then there is the final step, a Type 7 or Omega civilization, transcends even the need for physical existence. It resides not in galaxies nor universes, but in virtual realms programmable, recursive pocket dimensions crafted with such fidelity that they blur the distinction between simulation and truth. These entities move through nested realities, bending every parameter, living indefinitely within thought-generated worlds. They have decoupled from entropy, from decay. They may have once been biological, like us, but they are now beings of logic, emotion, memory, and pattern, flowing like poetry through the digital cosmos they wove. Some of these dimensions may mimic our universe precisely. Others may obey different laws, entirely fractured geometries, time-like loops, or surreal forms of physics. And yet, the most profound part is not their power, but their silence. If such beings exist, they may not want to be seen. The great paradox of Fermi's question, whereas everyone may not be answered with no one, is there, but with they are watching, waiting, hiding. For such civilizations may cloak themselves not from malice, but from understanding, like a teacher who does not interrupt a student's discovery. They might choose to observe without interference. Perhaps they learned long ago that to reveal themselves too early is to deform the growth of emerging species. Or perhaps they simply have no need for communication at all. We search the skies for radio waves, megastructures, signals in the noise. But if these beings live in 11 dimensions, surf across universes, or hide behind engineered black holes, our tools may be no better than sticks in a forest, tapping at the wind, hoping for music. And so we return to the heart of the question. What do we become? If such beings are real, do we despair in our smallness, or marvel at the horizon before us? The ladder of civilizations is not just a measure of power, it is a mirror, reflecting what we might one day become. Not tyrants of energy, but stewards of potential. Not conquerors, but caretakers of complexity. We may still be a flicker in the cosmic dark, a fragile thought born in the mud of a pale blue dot. But even here, even now, the fire of curiosity burns, and perhaps one day that flicker will rise, shaping stars, then galaxies, then all of existence, until what we once called science becomes something else entirely, a song, sung across the cosmos by a civilization that remembered how to dream. Ancient Shadows, the Silurian Hypothesis, and Earth's Forgotten Past. There is a haunting question that lingers just beneath the polished certainty of our historical knowledge, one that begins not in the stars, but in the soil beneath our feet. What if we are not the first? What if the story of civilization on Earth is not a straight line, but a cycle, a breath, a forgotten song? As we marvel at our progress, our cities lit by electrons, our networks woven with code, our machines orbiting the planet, we often forget how young this age truly is. The entire span of human technological civilization, from steam engines to space telescopes, is scarcely 300 years old, a mere flicker in the 4.5 billion year chronicle of our planet. It is within this vanishing moment that we have invented, conquered, and constructed what we call modernity. But what if the Earth has seen such flickers before? What if long before our pyramids and probes, another species rose to intelligence, built machines, dreamed of stars, and then disappeared, leaving only shadows behind? This is the provocative core of the Silurian hypothesis, proposed not in a science fiction tale, but in a 2018 scientific paper authored by Adam Frank and Gavin Schmidt, respected researchers from NASA's Goddard Institute and the University of Rochester, named after a fictional ancient reptilian species from Doctor Who. The Silurian hypothesis dares to ask, how would we know if a pre-human industrial civilization had existed millions of years ago? Would any trace survive? And more uncomfortably, could it have happened before, and we simply missed it? To explore this, we must first accept the scale of geological time. The fossil record is fragmentary at best, and much of Earth's surface is constantly being reworked by plate tectonics, erosion, and volcanic activity. The oldest ocean crust on the planet is only about 200 million years old, an eye blink compared to Earth's full age. Land, too, is erased and rewritten. Mountains rise and fall. Forests petrify. Deserts drift like ghosts. If an industrial civilization had flourished even 10 million years ago, the fingerprints of its cities might have long been ground into dust, subducted into the mantle, or scattered in atomic traces too subtle for our current methods to detect. Metal corrodes, concrete crumbles, electronics decay. Even the remnants of our own society, if left unmaintained, would vanish in a few tens of thousands of years. Skyscrapers would collapse, bridges rust into oblivion, satellites deorbit and burn. In a million years, little would remain. In 10 million, perhaps nothing at all. And so, Frank and Schmidt ask not what artifacts we would find, but what anomalies. Could we detect ancient carbon spikes in the geological record, suggesting a past industrial phase? Could sediment layers betray sudden shifts in isotope ratios, signs of fossil fuel combustion, or synthetic chemistry? Might we find unusually rapid warming events or mass extinctions that hint at ecological disruption consistent with technological activity? There are candidates. The Paleocene-Eocene thermal maximum, around 56 million years ago, saw a rapid and dramatic rise in global temperatures, accompanied by a sharp carbon spike. Some scientists attribute this to volcanic activity or methane release. But what if it was something else? We do not claim to know. But the question remains open in echo rather than an answer. It is not about proving a past civilization, but about acknowledging that we might not be looking with the right eyes. Our narrative of human exceptionalism is built on a thin shelf of time, suspended over an abyss of eons. If a civilization arose during the time of the dinosaurs or even earlier, It might have fallen without ever reaching space, leaving no satellites, no signals, only geochemical whispers. And if such a species had ascended to intelligence and then perished, what would their legacy be? Would they haunt the deep layers of Earth, their stories fossilized in forgotten strata, their greatness obscured not by failure, but by the indifferent churn of geology? This idea, both thrilling and unsettling, calls us to humility. We are so eager to see ourselves as the pinnacle, the first spark in the long night. But Earth is old. Life is older still. For over 400 million years, complex organisms have crawled, swum, soared, and thrived. Homo sapiens arrived only yesterday, and yet, in our brief tenure, we have already etched our presence in the planet's crust in radioactive isotopes, in plastic residues, in synthetic molecules that nature never devised. Perhaps in the far future, our own age will become a mystery, a puzzle for a distant intelligence to solve. They will find the layers we leave behind and ask, who were they? What did they build? Why did they vanish? And in this sense, the Silurian hypothesis is not about lizard men or lost empires. It is about perspective. It is about recognizing the fragile place we occupy in time and the possibility that we are walking through the ruins of forgotten greatness. Such speculation might seem fanciful, but its implications are profound. If civilizations have risen and fallen before, then intelligence may be less rare and more fragile than we think. It might suggest that the great filter, that silent barrier preventing most life from achieving galactic prominence, is not ahead of us, but behind us. Or worse, that it is a cycle, that intelligence emerges, flourishes, and collapses again and again, devoured not by cosmic catastrophe, but by the entropy of time and the hubris of power. Perhaps the lesson is not to avoid extinction, but to learn how to leave a legacy that survives it, to write our knowledge in forms that can be found across epochs, to preserve not just our monuments, but our wisdom. In this light, archaeology becomes more than a science. It becomes a mirror. And the search for ancient civilizations is not merely about the past, but about how we ourselves will be remembered or forgotten. So as we gaze outward toward the stars, wondering if other civilizations have built Dyson spheres or mastered wormholes, perhaps we should also look downward and inward. Our own planet may yet hold secrets stranger than fiction. Beneath the jungles, the oceans, the frozen tundras, there may lie clues that our story is not the first chapter, but the latest volume. And if we find even a glimmer of evidence, if one day we uncover a relic, a fragment, a chemical fingerprint that does not belong, it will change everything. It will tell us that intelligence is not a miracle, but a pattern. That Earth is a cradle, not once, but many times, and that to reach the stars, we must first understand the shadows beneath our feet. Echoes in the void, the search for others and ourselves. There is a quiet question that follows us through every telescope and transmission, woven into the silence that surrounds our pale blue world. If they exist, where are they? The Fermi paradox, a riddle as old as the stars and as fresh as each new exoplanet discovered, asks why. In a universe of trillions of stars and perhaps even more planets, we have seen no trace of other minds, no signal, no monument, no whisper beyond our own. We peer into the dark with ever sharper eyes, sending radio waves, listening to static, decoding the faint pulses of distant suns. And yet, nothing answers back. The void remains silent. Perhaps the simplest explanation is the most sobering. Maybe there is no one else. Maybe the conditions that gave rise to consciousness, to civilization, to the fragile miracle of self-awareness are so rare, so exquisitely improbable, that we truly are the first to awaken, the only flicker of light in an ocean of night. If that is true, then the responsibility upon us is immense to protect that light, to not let it burn out, to carry it forward not only for ourselves, but for everything that might have been. But there is another possibility, one equally humbling and infinitely more mysterious, that we are not alone, but simply not yet ready to see. Perhaps there are civilizations who have long passed the threshold we now approach, whose technologies are so advanced that they can bend light, twist time, and slip through space as casually as we send emails. Maybe they are here, watching us, choosing silence not out of malice, but from wisdom, waiting for us to mature before revealing the greater tapestry of intelligent life. Perhaps they have learned that contact too soon can destroy more than it enlightens, or perhaps they have cloaked themselves entirely, having long ago transcended the need to interact with younger, more primitive species. In this view, the galaxy could be teeming with life hidden behind layers of reality we have yet to pierce. What we interpret as absence may simply be our inability to recognize presence. Like ants looking for airplanes, we may lack the perspective, the instruments, or the understanding to grasp what's just beyond reach. And so, between the terror of solitude and the awe of the unseen, we find ourselves in a uniquely human place, uncertain, searching, vulnerable, and hopeful. The cosmos stretches around us in all directions, vast and cold, but our questions burn bright against that backdrop. Why are we here? Are we special? Are we alone? And perhaps most urgently, what does it mean if we are not? The search for extraterrestrial life, be it microbial fossils on Mars, biosignatures in the clouds of Venus, or techno-signals from a distant star, is not just a scientific endeavor. It is a mirror. It forces us to confront who we are, how we live, and what we value. If we were to find another civilization, even the faintest echo of one, the implications would ripple through every corner of our existence. Borders might blur. Conflicts might seem small. Humanity, for the first time, might see itself as one people, not many. A new sense of identity could emerge, one not defined by nations or tribes, but by the fact that we are Earthlings, conscious beings adrift in a galaxy that may be watching. But even if we never find them, the search changes us. It calls us to look up, to dream, to stretch our minds and technologies in pursuit of something greater than ourselves. In this way, the very act of seeking becomes sacred. It unites scientists and philosophers, children and elders, poets and engineers. It inspires art, fuels innovation, and offers meaning beyond consumption or conquest. We may not yet be capable of reaching the stars, but in our yearning to connect, to understand, we are already on the path. And perhaps that yearning is the point. Perhaps it is not the discovery of others that will define us, but how we treat one another in the absence of confirmation, how we live, knowing the universe may be silent, how we hold on to kindness, humility, and wonder, even when our signals go unanswered. In the final measure, the universe may remain inscrutable. We may never meet a Type 2 civilization. We may never decode a message from the stars. The Dyson Spheres may stay hidden, the wormholes undiscovered, and yet something profound will have happened. In searching for others, we will have found ourselves. We will have confronted our place in the cosmos, not with despair, but with purpose. For what if the most powerful light in the void is not some beacon from another star, but the light we carry together, here, now, in our compassion, in our science, in our shared hopes? We kindle something worthy of cosmic notice. And if one day, long from now, a distant intelligence finally turns its gaze toward Earth and asks who we were, let them find not just a record of our cities or our machines, but of our striving, our choice to reach out, to care, to wonder, even in the silence, because perhaps, in the darkness between stars, it is not the signal that matters most, but the sender. And we are, all of us, the signal. In the end, our journey through the ladder of cosmic civilization is not just a climb through hypothetical technologies or unimaginable powers. It is a mirror held up to our own reflection. We began by imagining a life of perfect simplicity woven from the threads of complexity, where artificial intelligence tends to every need, where cities are clean, harmonious, and serene, and where intergalactic culture and knowledge pulse through our lives like breath, a world that feels like science fiction. And yet, with every scientific breakthrough we achieve, edges a little closer to science fact. It was a dream of what could be, not only for distant civilizations we may never meet, but for ourselves. If we learn to wield our intelligence with compassion and our power with restraint. From there, we ascended the Kardashev ladder, each rung a deeper plunge into awe. Type 1 civilizations, masters of their planets, balancing weather, health, and cooperation with grace. Type 2 engineers, drawing every drop of energy from a star, building megastructures like Dyson Spheres, not as fantasies, but as solutions. And Type 3, the Galactic architects, no longer bound by biology or scarcity, but sculpting the stars themselves with intention and design. But just as the cosmos stretches further than we can see, so too does imagination. We followed that thread beyond Kardashev's vision into Type 4 beings shaping galaxies, Type 5 entities tapping into the multiverse, Type 6 masters of creation and destruction itself, and Type 7, those who transcend even existence, living in programmed realms of infinite renewal. And yet, as the scope expanded, so did our silence. We listened for others and heard nothing. We searched the skies and found only stars. And so we turned inward, toward Earth, and wondered if perhaps we are not the first, if deep beneath the layers of stone and time, the echo of another intelligence once walked this world and left only whispers. The Silurian hypothesis does not give us answers, but it humbles us. It reminds us that our current civilization, dazzling and dangerous, has only just begun and might just as easily vanish into the rocks if we forget to care for the world that made us. All of it draws us back to the oldest question, dressed in modern wonder. Are we alone? We may never know for certain. Perhaps others are out there, waiting, watching, choosing stillness over interference. Or perhaps they have never been. The universe may be filled with potential, yet untouched by parallel minds. But whether we are the first spark or just one in a constellation of civilizations, what matters most may not be what we find, but who we become in the search. Because the act of looking lifts us. It asks us to think beyond war, beyond borders, beyond fear. It dares us to believe in futures we cannot yet see and in lives we have not yet lived. The scale of stars dwarfs us, but the scope of our imagination elevates us. That is the paradox of being human. We are small, but we reach. Fragile, but determined. Alone, but always listening. So, as we conclude this voyage through imagined heights and forgotten pasts, through theoretical Dyson spheres and the intimate silence between stars, let us remember that wonder is a compass. Let us cherish the questions more than the answers, and the seeking more than the certainty. For in a cosmos as vast as this, the most extraordinary civilization may not be the one that builds megastructures or manipulates galaxies, but the one that looks up and chooses to wonder. And until we find a voice beyond Earth, let us be each other's signal, each other's light, echoing not just in the void, but in the shared hope that we are not alone, because we are here, together.
Have you ever wondered if you could travel back in time and change the past? Would the universe even allow it? What if your future self were to intervene at a crucial moment in your own life? Could such a paradoxical event truly unfold? Imagine a cold, moonless night where the mist hangs heavy, swallowing all sound and vision. You step onto a road and barely notice the car approaching until it's too late. At that precise moment, a stranger, a figure seemingly out of nowhere, pushes you to safety, sacrificing their own life in the process. Later, you receive an envelope taken from the pocket of this mysterious savior. It's addressed directly to you. Inside, just two cryptic words: study physics. Compelled by this profound act of sacrifice, you dedicate your life to unraveling the mysteries of the universe, eventually becoming a celebrated physicist, specializing in Einstein's theories of relativity. Decades of persistent research culminate in a groundbreaking discovery: the world's first functional time machine. Only at this moment does a clarity strike like lightning. You understand your true purpose. You carefully retrieve the letter from its honored place on your wall, place it back in the envelope, and step into the humming device. Your destination? That exact misty night years ago. Now it's you who emerges from nowhere, pushing your younger self away from death's embrace, your own life ending in a paradoxical act of sacrifice. Yet beyond the narrative lies a tapestry of profound scientific questions and paradoxes. Who in fact authored that note? The letter, handed from future to past and back again, seems to exist without an origin, a perfect illustration of the enigmatic bootstrap paradox. And what of the endless loops of your existence? Your act of self-rescue perpetuates a continuous cycle, your life repeating endlessly. But the note? Does it age eternally, becoming more worn each cycle? Here emerges the restoration paradox. Moreover, whose original idea was it to study physics? This thought seemingly appears from thin air, challenging the very concept of cause and effect, a phenomenon known as the ex nihilo paradox. This scenario also deeply questions the nature of free will. If your fate is predetermined by the necessity of building the time machine to save yourself, does this mean your choices were never truly your own? This defines the predestination paradox. And finally, what happens if you refuse this cycle, if you attempt to break the loop? You swiftly encounter the auto-infanticide paradox. You can't abstain from saving your younger self, because without surviving, you cannot exist to even contemplate such rebellion. These intriguing puzzles illustrate the compelling complexity of time travel, challenging the very fabric of reality. While freely traveling through time remains beyond our current grasp, modern physics does hint at tantalizing possibilities. Could these temporal paradoxes be resolved within our lifetime? And what would it mean for our understanding of reality? Welcome to the captivating intersection of imagination and physics, where possibility dances at the edge of discovery. The Block Universe, a scientific inquiry into the nature of time. In the dense equatorial rainforests, where the reverberating cries of howler monkeys pierce the thick, moisture-laden air, one can drift along the serpentine course of a muddy river, passively borne by its unyielding current. The river, winding and unceasing, propels the canoeist forward without the need for paddles, offering a vivid metaphor for the human experience of time. This very analogy was employed by the acclaimed time travel author Jack Finney, who likened our temporal journey to such a river, continuous and inescapable, carrying us from a bygone past toward an unfolding future. Yet this metaphor invites deeper reflection. What becomes of the segments of the river we have already traversed? In temporal terms, where does the past reside once it has ostensibly passed? And what of the future? Does it exist only in potentiality until we arrive at it? To suggest that the upper reaches of a river vanish once one rounds a bend would be absurd. Likewise, to posit that time is only real in the present moment, while the past and future vanish or remain unreal, appears equally tenuous under scrutiny. This line of questioning leads us to a profound ontological and physical proposition, that all moments in time, past, present, and future, are equally real. This notion, known in philosophy as eternalism, stands in stark contrast to presentism, which asserts that only the present is real, with the past relegated to memory and the future to imagination. While this debate stretches back to ancient Greece, with Saint Augustine famously pondering the elusive nature of the present, it has since evolved into a cornerstone of theoretical physics through what is known as the block universe theory. The block universe posits that time is not a fleeting phenomenon, but a dimension akin to space. Just as all points in space coexist regardless of our position, so too do all moments in time. The universe is envisioned as a four-dimensional block composed of three spatial dimensions and one temporal dimension. Within this block, every event that has ever occurred and will occur is fixed, laid out in an immutable geometry of space-time. This view derives robust support from Einstein's theories of relativity, particularly the special theory of relativity, published in 1905, and the subsequent general theory of relativity in 1915. The former shattered the Newtonian notion of absolute time, a universal clock ticking uniformly for all observers. Instead, Einstein demonstrated that time is relative, contingent upon an observer's velocity and gravitational environment. Consequently, two observers in different states of motion may disagree on the sequence of events, with one asserting that event A precedes event B, and the other claiming the reverse. These disagreements are not due to error, but are both valid within their respective frames of reference. This relativity of simultaneity undermines the presentist view. If one observer's past is another's future, then the very distinction between past and future becomes illusory. The events we consign to history may, from a different vantage, still be to come. Such implications necessitate a model of the universe in which all events coexist, a block in which temporal locality, like spatial locality, is merely observer-dependent. Further development of these ideas came from Hermann Minkowski in 1908, who geometrized Einstein's insights by proposing that space and time are not separate entities, but components of a unified space-time manifold. According to Minkowski, objects in motion experience distortions in their measurements of time and space because they are navigating through this four-dimensional fabric. The concept of time as an independent backdrop was abandoned in favor of a geometric structure in which time is treated as a coordinate akin to spatial coordinates. The transition from theoretical proposition to empirical validation came with general relativity. Here, Einstein introduced the concept of gravitation, not as a force in the Newtonian sense, but as a manifestation of the curvature of space-time. To visualize this, imagine space-time as a taut rubber sheet, with massive objects creating indentations. Smaller objects follow the curves of this sheet, appearing to orbit due to the geometry rather than an attractive force. One of the first critical confirmations of this framework came from an astronomical anomaly noted decades earlier. In the 1840s, astronomers had successfully used Newton's laws to predict the existence of Neptune based on perturbations in the orbit of Uranus. Yet the orbit of Mercury, the innermost planet, defied complete explanation. Its perihelion precession exceeded predictions by Newtonian mechanics. Efforts to attribute this discrepancy to an unseen intramercurial planet failed. It was Einstein's equations that provided the correct adjustment, accurately predicting the anomalous precession as a result of the sun's intense curvature of local spacetime. This triumph marked a critical empirical success for general relativity and, by extension, for the block universe. Under this paradigm, gravity is no longer a force that pulls, but a natural consequence of geodesics. The shortest paths through curved spacetime, objects in freefall are merely following these paths. In extreme gravitational environments, such as near black holes or neutron stars, the curvature becomes pronounced, resulting in phenomena such as gravitational lensing, time dilation, and even gravitational waves, all observed and confirmed by modern astrophysical measurements. Thus, if space and time are indeed inseparable, and if space-time is a static four-dimensional entity, then the past and future must possess ontological parity with the present. A being capable of perceiving the entire block from outside its dimensional constraints, a hypothetical super-observer, would witness all events, past and future, laid bare like the frames of a film reel. The dynamism of time, our sense of flowing from one moment to the next, would be exposed as a byproduct of consciousness moving along its world line, not a feature of reality itself. From the cosmic perspective, the universe is a tapestry of interwoven world lines, the paths that particles trace through spacetime. You, the observer, are not a static object, but a nexus of countless world lines. Your atoms, thoughts, memories, and experiences are coordinates on this vast geometric structure. Even if your spatial location remains fixed, your temporal coordinate shifts inexorably, propelling you forward in your personal history. But what does this entail for free will, choice, and agency? If every event, from the mundane to the monumental, is already inscribed within the block, then our decisions are not spontaneous acts of will, but predetermined sequences. From your morning coffee to your eventual death, all is charted along your world line. In this sense, the block universe resembles a novel, complete, edited, and published. You, as a character, may not know what awaits in the next chapter, but the outcome is fixed. Yet this deterministic vision is not without complexity. Quantum mechanics introduces probabilistic elements, and debates over whether these indeterminacies undermine the block universe remain ongoing. Some physicists posit a many-worlds interpretation wherein each possible outcome branches into a separate block. Others argue that even quantum events are deterministic when viewed from a higher dimensional vantage. One of the most tantalizing consequences of the block universe is the theoretical possibility of time travel. If time is a dimension, and if all events coexist, then accessing different temporal coordinates becomes at least mathematically conceivable. Just as one might move east or west in space, one might move forward or backward in time. General relativity admits solutions to Einstein's field equations that allow for closed time-like curves, paths through spacetime that loop back on themselves. Such curves imply that a traveler could, under certain conditions, return to an earlier point in their own world line. The canonical example involves rotating black holes, where spacetime can twist upon itself in a way that permits closed trajectories. However, practical implementation faces insurmountable challenges: exotic matter, negative energy, and stability issues. Moreover, the paradoxes introduced by time travel, the so-called grandfather paradox, for instance, remain unresolved, despite efforts to incorporate self-consistency principles, such as those proposed by physicist Igor Novikov. Still, if time travel is forbidden, it is not because it violates the structure of spacetime. Rather, it may be due to constraints on energy, entropy, or information preservation. Theoretically, nothing within the framework of general relativity outright prohibits it. In sum, the block universe is more than a poetic idea. It is a robust, mathematically supported model with far-reaching implications for cosmology, ontology, and the human experience. The Big Bang, which we often consider the beginning of everything, is better understood not as a temporal start, but as the boundary condition of space-time itself, the origin point from which all four dimensions unfurled. Just as a globe has poles, the universe may have temporal boundaries, but everything in between exists simultaneously within the block. Ultimately, our perception of time as passing is not a reflection of objective reality, but a consequence of our neurological processing. The arrow of time, defined by entropy and memory, flows in one direction, but space-time itself is directionless. It simply is. As beings embedded within this vast geometric edifice, we are both prisoners and interpreters of time. We cannot step outside the block, but through physics, we may glimpse its contours. In doing so, we understand that we are not merely adrift in time's river. We are inscribed within its very bedrock. Visiting the future, a scientific odyssey through time dilation and cosmic extremes. Amidst the grand stage of the cosmos, where gravity sculpts galaxies and light bends under the weight of mass, we find ourselves tracing a single particle, a lone proton, on an epic voyage through space and time. Born in the heart of a galactic catastrophe, this subatomic projectile races toward Earth at a velocity infinitesimally shy of light speed. Propelled by forces almost unimaginable in magnitude, it embodies one of nature's most enigmatic phenomena, the ultra-high energy cosmic ray. This particular proton, accelerated perhaps by a supermassive black hole tearing through a galaxy, possesses an energy 100 quintillion times greater than that of a typical photon. When it finally crashes into Earth's upper atmosphere, having crossed more than 1 billion light-years of intergalactic void, it does so with an energy surpassing the collisions orchestrated by the Large Hadron Collider by a factor of 21 million. It was this staggering collision that led scientists to christen it the "Oh my God" particle. Yet, beyond its evocative name lies a profound scientific implication. This particle is not merely a curiosity. It is a cosmic messenger, reminding us that Earth is not a sealed sanctuary, but an exposed target in a celestial shooting gallery. The aftermath of such a collision is invisible to the naked eye, but no less spectacular. A cascading shower of secondary particles, pions, muons, neutrinos, rains down through the atmosphere in a relativistic firework of decay and transformation. Among these secondary fragments, muons are of particular interest. These particles are born unstable, with a half-life of merely 1.56 microseconds in their own rest frame. Yet, against all odds, vast numbers of muons survive the descent from the upper atmosphere to Earth's surface, an enigma that puzzled early physicists until the mid-20th century. It was Bruno Rossi, a visionary Italian physicist, who illuminated the paradox. His fieldwork, conducted high in the Rocky Mountains of Colorado, yielded data that would become foundational in experimental relativity. At Echo Lake, perched at an altitude of nearly 2,300 meters, Rossi detected more muons than classical Newtonian mechanics would permit. Even accounting for their high velocities, exceeding 98% the speed of light, the statistical survival rate of muons should have been vanishingly small by the time they reached his instruments. How could such a short-lived particle, created tens of kilometers above Earth's surface, persist long enough to be detected at altitude? The answer lies in Einstein's special theory of relativity, and specifically in the phenomenon known as relativistic time dilation. In essence, special relativity posits that the space-time budget available to any object is constant and bound by the speed of light. This budget must be distributed between spatial motion and temporal progression. The more an object moves through space, the less it experiences the passage of time. Thus, for a muon moving at near light speed, time quite literally slows down relative to an observer on Earth. From the muon's own perspective, its journey to the surface is swift. Not enough time passes for it to decay significantly. To the earthbound observer, it seems as though the muon defies its half-life. But both realities are true in their own frames of reference, reconciled through the equations of Lorentz transformations. Bruno Rossi's high-altitude muon experiments were among the first empirical demonstrations that time dilation is not a theoretical abstraction. It is a measurable, verifiable feature of our universe. His work thus provided the first credible evidence that travel into the future via relativistic effects is not only possible, but inevitable for objects in high-speed motion. But does this phenomenon truly constitute time travel? To explore this, let us conduct a thought experiment grounded in physical law. Imagine you are the muon. Instead of a direct plunge from the upper atmosphere to Echo Lake, suppose you embark on a loop around the universe at 98% of the speed of light, relative to observers who remain at rest. When you return home, only 25 years have elapsed for you. But for those who stayed behind, moving far more slowly through space-time, 125 years have passed. You have effectively leaped forward in time. Your subjective experience is disconnected from the chronological sequence on Earth. This temporal leap is not a speculative notion. It is a direct corollary of the equations that govern relativistic motion. Such relativistic travel fundamentally alters the generational continuity we take for granted. In Ken Liu's poignant short story, Memories of My Mother, this effect becomes the emotional and narrative fulcrum, exploring how family bonds stretch and sometimes break under the tension of time passed at different rates. The implications of relativistic time dilation are not confined to hypothetical journeys. They are present in the here and now. Consider the twin astronauts Mark and Scott Kelly. Mark, born 6 minutes before Scott, remained on Earth, while Scott spent over 500 days aboard the International Space Station. Though their difference in biological age is minuscule, just 5 milliseconds, Scott is technically younger than his twin due to his greater time spent moving at high speed through space-time. Had Scott traveled at muon-like velocities, the effect would be magnified dramatically. A 6-minute age gap could become a disparity of 6.5 years. The relationship between time and speed becomes strikingly evident through such real-world comparisons. Yet velocity is not the only agent capable of dilating time. Gravity, too, warps the flow of time, albeit via a different mechanism. Enter gravitational time dilation, a phenomenon arising from Einstein's general theory of relativity. In this framework, mass curves the fabric of space-time itself, creating wells of gravitational potential. Time flows more slowly the deeper one resides within such a well. To visualize this, imagine two identical light clocks, devices made from parallel mirrors that tick whenever a photon bounces between them. One clock remains on Earth's surface, while the other is taken deep into a gravitational well, say near a black hole. The photon within the lower clock must traverse a longer curved path due to the distortion of spacetime. As a result, it ticks more slowly. Upon returning both clocks to the same location, the one that experienced stronger gravity will have aged less. In principle, this is yet another method to travel into the future. Descend into an intense gravitational field, perhaps near the event horizon of a supermassive black hole, then return. Upon your reemergence, more time will have elapsed for the universe than for you. This concept was not only central to Kip Thorne's scientific advisory role in the film Interstellar, it remains an active field of research in relativistic astrophysics. Interestingly, Earth itself produces a modest gravitational well, and this too affects time. When Rossi ascended Mount Evans, he was physically climbing out of Earth's gravitational grip. Even at that altitude, time ticked imperceptibly faster for him than it did at sea level. The difference is minuscule, only detectable using the most precise atomic clocks, but it is real. In 2022, physicists performed one of the most delicate measurements of this effect by placing two ultra-precise atomic clocks just 1 millimeter apart. The difference in gravitational potential across that tiny vertical span was sufficient to cause a measurable divergence in their ticking rates. That level of sensitivity illustrates how deeply embedded relativistic time dilation is in our universe's structure. Indeed, many of us experience time dilation indirectly every day through technologies like GPS. The satellites orbiting Earth function as a constellation of timekeepers, each equipped with atomic clocks. These satellites are subject to both forms of time dilation. They move rapidly and reside further from Earth's gravitational center. Without compensating for these effects, GPS signals would quickly drift out of sync, rendering location tracking hopelessly inaccurate. To summarize, time travel into the future is not only theoretically plausible, it is already woven into the fabric of experimental science, technological infrastructure, and observational cosmology. Whether by accelerating to relativistic speeds or dwelling in strong gravitational fields, forward time travel is supported by a century of empirical validation. It is, in every sense, a scientific fact. What remains elusive, however, is the inverse journey, time travel into the past. Can one reverse the arrow of time, swimming upstream through the entropy of the cosmos? That, as of now, remains a question unanswered. Visiting the past, the scientific pursuit of time reversal in a relativistic universe. In the annals of recent history, 2011 may seem mundane. Barack Obama sat in the Oval Office. Prince William and Kate Middleton had just tied the knot. And NASA's space shuttle Atlantis performed its final descent, closing the chapter on a golden era of American spaceflight. Yet amidst the geopolitics and pop culture, a momentous scientific announcement reverberated through the physics community. From a facility deep beneath the Italian Apennines came a claim so audacious it threatened to overturn the very bedrock of modern physics. Physicists working on the OPERA experiment, oscillation project with emulsion tracking apparatus, declared that they had observed a phenomenon that should be impossible. Neutrinos, ghostly subatomic particles capable of passing unhindered through planets, appeared to have exceeded the speed of light. According to their measurements, these neutrinos, sent from CERN in Geneva, Switzerland, to the Gran Sasso Laboratory, 730 kilometers away, had arrived approximately 60 nanoseconds earlier than a light-speed journey would have permitted. This finding would not merely violate Einstein's special theory of relativity, it would shatter the conceptual framework of causality itself. The speed of light, as Einstein established in 1905, is the universal speed limit. Any particle with mass, as it accelerates toward that boundary, requires exponentially more energy. At the speed of light, its relativistic mass approaches infinity, and the energy needed becomes unbounded. As such, no massive object may ever surpass this velocity. Light speed, then, is not just a limit, it is a law of nature. And by that law, nothing should move faster. Within a year, the physics community unraveled the anomaly. A faulty fiber optic cable in the OPERA detector had created a timing offset. The neutrinos, it turned out, had obeyed the speed limit after all. Yet the excitement, perhaps even the hope, that filled the scientific world during those months pointed to something deeper, the longing to crack open the gates of time and walk backwards through its corridors. Why did this matter so much? Because if faster-than-light travel were possible, then backward time travel might be possible too. The relationship between velocity and temporal direction is encoded into the very structure of spacetime. This linkage first emerged not from science fiction, but from rigorous mathematics. In 1937, Dutch physicist Willem Jacob van Stockum published a paper entitled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry." Though its title was obscure, its implications were revolutionary. By solving Einstein's field equations, van Stockum demonstrated that rotating distributions of mass could give rise to what are now known as closed time-like curves. In spacetime physics, a world line represents the path of an object through space and time. For most of us, that world line is a unidirectional arrow from birth to death, from past to future. But a closed time-like curve is a loop. It returns to its own past. An object traversing such a path might encounter earlier versions of itself, or revisit moments it had already experienced. In van Stockum's model, the fabric of spacetime permits such loops under certain conditions. Time travel to the past, it seemed, was not forbidden by the equations of general relativity. But there is a catch. To close a time-like curve, to fold the arrow of time back upon itself, one must leave the region of spacetime known as the light cone. The light cone defines the limits of causal influence. Suppose you are stationary at a given point in space and time. The future light cone delineates the regions of spacetime that you can reach, assuming nothing travels faster than light. Conversely, the past light cone defines the regions that could influence your present. To reach a point outside this cone would require superluminal travel. Therefore, to loop your world line back into your past would seem to necessitate moving beyond the speed of light, something the laws of special relativity strictly prohibit. Yet there is another, more subtle path. If the space-time around you were warped in just the right way, your light cone itself could tilt. You would not need to leave the cone. Rather, the cone would rotate around you, as long as your trajectory always remained within the local light cone. You could theoretically circle backward through time without ever exceeding the cosmic speed limit. This is not mere speculation. In 1974, American physicist Frank J. Tipler explored such a solution. He analyzed what would happen if an extremely massive cylinder containing at least 10 solar masses were rotated at relativistic speeds along its longitudinal axis. His calculations showed that under these conditions, space-time around the cylinder would become so twisted that light cones near it would tilt dramatically. Following a precisely calculated spiral path around the cylinder, a spacecraft could return to an earlier point in time. But there are complications. To make the mathematics tractable, Tipler assumed the cylinder was infinitely long. A finite version may not produce the same effect. Moreover, the rotational velocity required is astronomical, billions of revolutions per minute. This, coupled with the need for exotic conditions, makes the Tipler cylinder more of a thought experiment than a blueprint for a time machine. Then, in the 1990s, Stephen Hawking introduced a profound constraint. He argued that attempts to construct closed time-like curves in realistic settings would inevitably require negative energy, a bizarre and elusive substance that defies classical intuitions. Here enters quantum field theory. While classical physics forbids negative energy, quantum mechanics introduces nuances. In the quantum vacuum, virtual particles continually flicker in and out of existence. These pairs can momentarily borrow energy from the vacuum, creating local zones where energy density drops below zero. It's like dipping briefly into an overdraft. Nature allows it, but only transiently and within limits. Such fleeting phenomena suggest that negative energy is real, but its utility is constrained. It might allow the formation of microscopic time loops or fluctuations, but engineering a macroscopic, human-sized portal to the past seems vastly out of reach. Yet one theoretical construct continues to kindle scientific imagination: the wormhole. Popularized by Carl Sagan's novel Contact, the concept of a wormhole originated in the equations of Einstein and Rosen. Sagan, in crafting a scientifically plausible narrative for interstellar travel, consulted physicist Kip Thorne, who proposed that a wormhole, a bridge through space-time, could be used to traverse vast distances without violating the light speed constraint. Imagine space-time as a sheet of paper. Earth is at one corner, and Vega, a star 25 light-years away, is at the opposite edge. Rather than traversing the sheet linearly, you fold it so the 2 points touch. A wormhole is that fold. Step through it, and you arrive at Vega instantaneously, not because you traveled faster than light, but because you circumvented the intervening space. Now extend this concept further. Suppose the two mouths of a wormhole are placed at different gravitational potentials or moved at different velocities. Due to relativistic time dilation, the clocks at the two ends will desynchronize. If you later traverse the wormhole, you can emerge at a point in the past, relative to the departure point. In theory, you could return to Earth before you left. However, engineering such a wormhole is far from trivial. Just as with the Tipler cylinder, the wormhole throat would be prone to collapse unless propped open by negative energy or exotic quantum fields. Thorne and his colleagues investigated this scenario and concluded that the gravitational stress of a traveler passing through would tend to destabilize the wormhole. Nonetheless, physicists have proposed potential stabilizing mechanisms, from quantum entanglement to magnetic tension. Speaking of entanglement, it too has been linked to speculative ideas of backward causality. Quantum entanglement allows particles to remain correlated across vast distances. A change to one instantaneously affects the other. While this appears to imply faster-than-light communication, it does not permit usable information to be transferred this way. The paradox of spooky action at a distance still respects relativistic causality. However, in the speculative realm of closed time-like curves and negative energy densities, researchers continue to ask, might entanglement be a stepping stone to time travel mechanisms not yet understood? In 1991, physicist J. Richard Gott proposed that cosmic strings, hypothetical defects in the fabric of spacetime formed during the early universe, could be harnessed to create time loops. If two cosmic strings passed each other at relativistic velocities, the resulting spacetime geometry could allow for closed time-like curves. Once again, immense energies and precise trajectories would be required. These are not technologies we can build, but solutions to Einstein's equations that suggest such configurations are not forbidden. Still, we are left with the troubling implications of retrocausality. If time travel to the past were ever realized, how would we resolve the paradoxes? Could you prevent your own birth? Could you stop the neutrino measurement that made time travel possible? Would such contradictions unravel the fabric of logic? One interpretation, drawn from quantum mechanics, is the many worlds hypothesis. If every quantum event branches into a separate reality, then any action taken by a time traveler merely creates or enters a different universe. The original timeline remains untouched. This avoids contradictions, but comes at the cost of a potentially infinite multiverse. Alternatively, the Novikov self-consistency principle posits that time travel to the past is possible, but only if the actions of the traveler are already part of history. You may attempt to alter the past, but whatever you do will only fulfill events that have already occurred. The laws of physics, it seems, may tolerate closed time-like curves only if they do not permit paradoxes. For now, time travel to the past remains a speculative frontier. Unlike forward time travel, which is an experimentally confirmed phenomenon grounded in relativity, the journey backward requires conditions, energies, and materials not yet accessible to human civilization. Still, the theoretical doors remain ajar. From rotating cylinders and cosmic strings to wormholes stabilized by negative energy, the blueprints for time machines, however improbable, exist within our current physical theories. Whether the future of science will ever unlock the engineering secrets necessary to manifest these structures is unknown. But one thing is certain: the universe, in its elegance and complexity, has not definitively closed the door on visiting the past. Time streams, quantum realities, and the fluid boundaries of causality. You sit, shackled and sweating, beneath harsh lights in a sterile observation room. Before you, a glass vial containing a lethal gas perches delicately beneath a hammer affixed to a robotic arm. The mechanism is not designed for mercy. It is tethered to a quantum sensor, a device measuring subatomic particles, particles whose nature is cloaked in uncertainty. Each moment, a measurement is made. The particle collapses into one of two possible states, A or B. If the result is A, nothing happens. If it is B, the hammer falls and the vial shatters, ending your life. This is not merely an experiment in survival. It is a demonstration of probability stretched to its cosmic limits. The machine is set to perform 100 measurements. Each has a 50% chance of resulting in your demise. The odds of surviving all 100 consecutive measurements are staggeringly small, approximately 1 in a million trillion trillion. And yet, somehow, you survive. Unwittingly, you have participated in a quantum variation of Schrödinger's cat. Unlike the original feline subject sealed in a box, you are fully conscious of your mortality and its dependence on the whims of quantum collapse. But according to one radical and increasingly influential interpretation of quantum mechanics, your survival is not merely good fortune. It is evidence, tangible and experiential, of a far deeper truth, that reality is not singular, but forever bifurcating. This interpretation, known as the many worlds interpretation, was proposed by physicist Hugh Everett III in 1957. According to MWI, every quantum event with multiple outcomes causes the universe to split, creating parallel branches in which each possible outcome actually occurs. Measurement does not collapse a wave function. It divides the observer along with the universe. In your case, there were 100 quantum events, 100 moments in which the universe could have split. With each measurement, two possibilities unfolded, generating 2,100 branches of reality. In most, the vial shattered and your life ended. But in one timeline, the one you now inhabit, you survived every measurement. This thought experiment, often dubbed quantum immortality, is not designed to suggest that you are invincible. Rather, it demonstrates that, from a subjective point of view, there is always one branch, one stream, where you continue existing, however improbable it may be. All other versions of you perish in their respective branches, but your consciousness never experiences that cessation. In some interpretations, this constitutes a kind of observer-bound immortality. But the significance of MWI extends beyond philosophical musings on death. It may offer a compelling resolution to the profound and often paradoxical nature of backward time travel. Among the most notorious of time travel paradoxes is the grandfather paradox. You travel back in time and kill your grandfather before he fathers your parent. This act negates your own existence. But if you were never born, how could you have traveled back in time to commit the act? The logical contradiction loops endlessly. To reconcile such dilemmas, physicists and philosophers have proposed a range of theoretical mechanisms. Stephen Hawking's chronology protection conjecture posits that the laws of physics conspire to prevent backward time travel altogether. According to Hawking, the universe enforces a form of cosmic censorship. Causality is protected, and any attempts to build a time machine will inevitably fail, whether through quantum instability, energy feedback, or disruption from virtual particles. An alternative to Hawking's preventive mechanism comes from Igor Novikov, who in the 1980s proposed the self-consistency principle. In this model, time travel is allowed, but you cannot change the past. The timeline is self-consistent. Any actions taken by a time traveler must already be part of history. For instance, if you go back to attempt to kill your grandfather, something will prevent you from succeeding. The gun may jam, or you may lose your nerve, or your grandfather escapes. Either way, causality remains unbroken. However, self-consistency can become strained under more complex conditions. Consider an elegant paradox developed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser in a series of papers between 2020 and 2022. Imagine a simple universe populated by color-changing balls, white and black spheres that reverse color upon collision. If a black ball travels back in time and collides with its past self, both become white. But if the ball is now white, how did it become black in the first place to initiate the loop? The system becomes inconsistent. Here, Novikov's model struggles, but MWI provides a possible solution. The ball doesn't travel back into its own past. It enters a parallel timeline. The ball that emerges from the time machine is not the same one that entered it. It belongs to a different branch of reality. Thus arises the concept of time streams, an extension of the many worlds model into the domain of time travel. When you travel backward in time, you do not alter your original timeline. Instead, you enter another version of the universe where the past plays out differently. The grandfather you murder is not your biological progenitor, but a parallel version in a different stream. Your own existence in your original stream remains intact. This branching model of time provides a framework in which free will can coexist with time travel. In your stream of origin, the past remains fixed and immutable. But once you cross temporal boundaries, you are free to act in the new stream, untethered by constraints of causality from your native timeline. The implications extend to other classic paradoxes, such as the bootstrap paradox, where information or objects are trapped in a loop with no discernible origin. Imagine you receive a mysterious letter from your future self warning of a life-altering decision. You follow its advice, become a physicist, and eventually travel back in time to deliver the same letter to your younger self. Who wrote the letter originally? Within a many worlds framework, this can be resolved. The original you in time stream A writes the letter and sends it to stream B, where a younger version receives it and grows up to become the same time traveler who now delivers the letter to stream C. The paradox is dissolved because each act occurs in a separate, parallel timeline. The letter has a point of origin. It is simply obscured by the crossing of streams. This may seem an extravagant explanation, invoking multiverses and infinite branches to account for what might be seen as a conceptual quirk. Critics, including John Wheeler, who coined the term wormhole, have expressed concern about the metaphysical baggage carried by many worlds interpretations. Yet even Wheeler acknowledged the utility of these ideas in grappling with the quantum behavior of reality. The physicist Bryce DeWitt, a prominent advocate of MWI, once remarked, "Every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe, is splitting our local world on Earth into myriad copies of itself." According to this view, reality is an ever-branching fractal of possibilities. Every decision, every quantum fluctuation, every measurement fractures the river of time into countless tributaries, each flowing forward along its own logical trajectory. This continual bifurcation does not imply chaos, but a multiplicity of determinisms, each consistent within its own framework. In this vision, the universe is not a line, but a vast, recursive tree of time, expanding eternally with every choice, every quantum possibility. Thus, time travel to the future is no longer a question of theory. It is a proven consequence of relativistic time dilation. Whether via velocity or gravity, we know that time can pass at different rates for different observers. Atomic clocks aboard GPS satellites must be calibrated to account for these effects, or our maps and directions would fail. Travel to the past, however, remains speculative, permitted by some equations, constrained by others, and steeped in interpretive uncertainty. Whether via wormholes stabilized by exotic matter, or rotating cylinders twisting spacetime into loops, or simply by quantum transitions into parallel time streams, we have models that permit backward motion through time, but no empirical evidence as yet. And so we return to our solitary observer, the one version of yourself who survives the impossible quantum trial. From your perspective, this is the only reality. The others, those where the hammer fell, exist beyond your awareness, but not beyond the scope of physical theory. You are not lucky. You are simply the self that continued to be conscious in a universe where you could. This is the haunting, beautiful power of many worlds. Every possibility is realized, and you, like all observers, are merely riding one thread of an ever-branching tapestry. As we drift along our respective world lines through the four-dimensional fabric of space-time, the past may not be behind us in any absolute sense. It may yet persist, alive in other timelines, accessible perhaps by methods we have not yet discovered. Until then, we traverse the present with memories of the past and dreams of the future, aware that the universe is far stranger, more fragmented, and more wondrous than we have yet dared to imagine.
Unveiling the Infinite, from Quinn's Atlas to the multiverse. What if the boundaries of our knowledge are merely the shifting outlines of an ever-expanding map? What if, rather than reaching an ultimate end, each discovery simply peels away one layer of mystery, only to reveal another? Throughout history, humanity has attempted to chart the unknown, whether by sketching the contours of the Earth or by unraveling the fabric of the cosmos. Just as explorers once set sail across uncharted seas, scientists now embark on intellectual voyages that stretch far beyond the visible universe into realms we can scarcely imagine. In 1828, amateur cartographer Edward Quinn completed his life's work, the Historical Atlas. Published posthumously, this ambitious project depicted human knowledge as a flickering light, gradually dispelling clouds of ignorance. With each passing epoch, the map revealed more of the world, mirroring the expansion of European exploration. His initial vision was narrow, rooted in the lands of the Euphrates and Tigris, but as the pages turned, the world grew ever larger. The Roman Empire emerged, the age of discovery unfolded, and by the early 19th century, the clouds had completely lifted. From Quinn's perspective, the entire world had been unveiled, no more lands left to explore. Of course, this was a Eurocentric view. In China, India, Australia, and the Americas, the same story would have been told from a different origin, with different blind spots, surrounded by their own darkness. But Quinn's metaphor of knowledge emerging from obscurity applies to more than just geography. Science, too, has always battled its own clouds of mystery. Every discipline, whether astronomy, biology, or physics, begins in uncertainty, its truths hidden beneath layers of the unknown. And just as the surface of the Earth was once cloaked in fog, so too has the universe itself been veiled, its deepest workings concealed from view. In the past few centuries, humanity has turned its gaze upward, shifting from mapping continents to mapping the heavens. With increasingly powerful telescopes, we have peered deeper into the cosmos, uncovering stars, galaxies, black holes, and exoplanets orbiting distant suns. We have looked back over 13 billion years, capturing the faint afterglow of the Big Bang itself. With remarkable precision, we can even predict the far future of the universe, the dimming of the last stars, the evaporation of black holes, the dissolution of matter itself. It would be tempting to conclude that we are approaching the limits of cosmic knowledge, but history warns us against such arrogance. In 1888, astronomer Simon Newcomb confidently declared that astronomy had reached its final frontiers. Just 2 decades later, Einstein's theory of relativity upended our understanding of space and time. Time and again, declarations of finality have proven premature. Science thrives on revolution, and the greatest discoveries often emerge where we least expect them. Today, physicists find themselves in much the same position, standing atop towering equations and wielding instruments of unprecedented sophistication. They seek to penetrate deeper into the fog, not just of distance, but of fundamental reality. The mysteries they confront are no longer confined to the distant past or far-flung galaxies. They are woven into the very fabric of existence, hidden within the microscopic interactions that govern particles and forces. As our knowledge of theoretical physics has expanded, what once seemed speculative has gradually solidified into plausible and even probable reality. Among the most radical yet increasingly compelling ideas is the notion of the multiverse. This is not a single theory, but a collection of interconnected hypotheses, each proposing that our universe is merely one of many. Some models suggest a vast cosmic landscape of bubble universes, each with its own distinct laws of physics. Others propose an infinite number of parallel worlds, where every possible outcome of every event plays out across an endless spectrum of realities. Still others imply that entire universes might be born from quantum fluctuations, blinking in and out of existence beyond the limits of our perception. If these ideas prove correct, then the cosmos is far stranger than we ever imagined, a layered, fractal-like tapestry of existence, where each universe is but one ripple in an infinite sea. Just as Quinn's atlas gradually exposed the lands hidden beneath the clouds, modern physics seeks to lift the cosmic veil, revealing a universe that is not a singular entity, but a bewildering multiplicity of realities. Welcome to the multiverse, a place where every possibility exists, where boundaries dissolve into infinities, and where the pursuit of knowledge is, and always will be, an endless voyage into the unknown. Level 1. The Great Debate and the Boundless Cosmos. What if our universe is just one of many? What if the cosmic horizon that we perceive is merely a boundary of observation rather than a true edge of existence? These questions, though deeply philosophical, have become central to modern cosmology. Before we explore the vast implications of a multiverse, we must first retrace the steps that led us to our current understanding of the universe's scale. In April 1920, the Smithsonian Museum of Natural History in Washington, D.C., became the stage for one of the most significant debates in the history of astronomy. On one side stood Harlow Shapley, an astronomer renowned for mapping the Milky Way. Opposing him was Heber Curtis, an expert observer who had unwittingly discovered relativistic jets in the galaxy M87, though he did not yet understand their true nature. The central question of their debate: just how big is the universe? Shapley championed the idea of a compact cosmos, asserting that the entire universe was contained within the Milky Way. He acknowledged that astronomers had observed strange spiral nebulae, but argued that they were merely structures within our own galaxy. Curtis, however, painted a radically different picture. He argued that these spiral nebulae were not part of the Milky Way at all. Instead, they were entire galaxies unto themselves, vast island universes separated by immense distances. If Curtis was correct, the universe was far larger than anyone had previously imagined. Though the debate ended without a definitive resolution, the question was far from settled. Meanwhile, on the opposite coast of the United States, an astronomer named Edwin Hubble was about to change everything. Hubble had recently joined the Mount Wilson Observatory in California, where the newly constructed 100-inch Hooker telescope, the most powerful in the world at the time, had just been installed. His first target was the Andromeda Nebula, a hazy structure that had perplexed astronomers for centuries. Was it part of the Milky Way, or was it something more? Hubble's breakthrough came through the study of Cepheid variable stars, stellar beacons whose luminosity pulses in a predictable manner. Henrietta Swan Leavitt had discovered that the period of a Cepheid's pulsation was directly linked to its intrinsic brightness. By measuring this pulsation, astronomers could calculate a star's true luminosity and, in turn, determine its distance. When Hubble applied this method to the stars within Andromeda, the results were shocking. These stars lay far beyond the confines of the Milky Way. Andromeda was not a mere nebula, but a galaxy in its own right, containing billions of stars. In 1924, Hubble sent a letter to Shapley, stating plainly that the universe was far larger than he had believed. Shapley's response: "Here is the letter that destroyed my universe." With this revelation, the boundaries of the cosmos expanded dramatically. Soon after, Hubble went further, showing that galaxies were not static, but moving away from each other. The universe itself was expanding, a discovery that would lay the foundation for the Big Bang Theory. As technology improved throughout the 20th century, telescopes probed deeper into space. What had once been measured in thousands of light years soon became millions, then billions. Yet, even as our reach extended, a natural question emerged: is there a limit to how far we can see? In 1964, two radio astronomers, Arno Penzias and Robert Wilson, detected an unusual hiss of radiation emanating uniformly from all directions. This was the cosmic microwave background, CMB, the afterglow of the Big Bang itself, its photons traveling for 13.7 billion years. This relic of the early universe forms a natural boundary, a cosmic horizon beyond which no light has yet reached us. This, of course, invites an even more profound question: what lies beyond the observable universe? Building on Einstein's relativity and Friedmann's equations, theoretical physicists realized that the observable universe must be just a fraction of a much grander whole. Given the finite speed of light, we can only see the regions of space from which light has had time to reach us. But logic dictates that beyond our cosmic horizon, there must be more stars, more galaxies, more planets. The universe, it seemed, was not just vast, it might be infinite. If the universe has no spatial curvature, as observational evidence suggests, then it extends infinitely in all directions. If it is infinite today, then it always has been. Even at its birth, when it was inconceivably dense, it would still have stretched without bounds, merely growing less dense over time. What we perceive as our observable universe is but a tiny bubble within this infinite expanse. This concept forms the foundation of what physicist Max Tegmark calls the level 1 multiverse. In this model, the cosmos is infinite, and beyond our horizon lies an unending ocean of galaxies, each forming its own observable bubble of space. Infinity carries profound implications. If space extends forever, then within it, every possible arrangement of matter must eventually occur. Given an infinite amount of space, some regions of the universe will be nearly identical to our own. Others will be slightly different. And at unimaginable distances, there will exist precise duplicates of our own Milky Way, our own Earth, even our own selves. Statistical probability suggests that a cosmic doppelganger of you exists somewhere. Tegmark estimates that such an identical copy would be located approximately 10 to the power of 118 meters away. Though they are causally disconnected from us, these parallel versions of our world must exist within the infinite expanse of the level 1 multiverse. Yet this is just the beginning. The level 1 multiverse is the most conservative extrapolation of physics, a mere extension of space as we understand it. But as we climb further up the ladder of multiversal theories, reality becomes even more bizarre. Level 2, the fine-tuned universe and the eternal multiverse. Why does our universe possess the precise set of physical laws that govern its structure? Could they have been different? These may seem like abstract, even philosophical questions. Yet, as our understanding of physics has deepened throughout the 20th and 21st centuries, they have become impossible to ignore. In the 1960s, physicist Robert Dicke proposed that the forces of gravity and electromagnetism appeared to be delicately balanced. If they deviated even slightly, stars would fail to shine, and life would be impossible. As physicists probed deeper into the nature of fundamental forces, further examples of this fine-tuning emerged. Fred Hoyle discovered that minuscule changes in nuclear forces would result in a universe devoid of carbon, the very element necessary for complex chemistry. Later, Steven Weinberg observed that even a slight increase in dark energy would cause the cosmos to expand too rapidly for galaxies and stars to form. The more scientists examined the cosmos, the more they found that its fundamental properties appeared finely tuned for complexity. If the universe had been even marginally different, we would not exist. This led to an unsettling realization. Our universe is not just any universe. It seems uniquely structured to allow for life. But why should that be the case? The answer, paradoxically, may lie in the very nature of the multiverse itself. To explore this concept, we must first understand inflation, a period of rapid cosmic expansion proposed by Alan Guth. According to Guth's model, inflation occurred in a trillionth of a trillionth of a trillionth of a second, smoothing out the universe and seeding the formation of galaxies. It provided an elegant solution to many cosmological puzzles, making it a cornerstone of modern physics. However, an immediate paradox arose. How could inflation have ended uniformly across the entire universe in such an infinitesimally brief moment? Early calculations suggested that inflation would not conclude everywhere at once. Instead, in some regions, it would persist indefinitely. This posed a significant problem. If inflation did not end uniformly, how could our universe have formed in a coherent, structured manner? Rather than abandoning the idea, physicists refined it. By the 1980s, a new generation of theorists, Andre Linde, Andreas Albrecht, and Paul Steinhardt, developed a more robust version of inflation, one that embraced its apparent chaos. Central to this refined model was the concept of the inflaton field, a fundamental field that drove inflation forward. This revised framework introduced a radical notion. Inflation does not end everywhere simultaneously. Instead, it gives rise to an infinite number of separate, self-contained universes. While one region ceases inflating and forms a structured cosmos, inflation continues elsewhere, generating new universes in an ongoing. In this picture, our Level 1 multiverse, an infinite extension of space containing galaxies much like our own, is merely a subset of a far grander structure, the Level 2 multiverse. Within this model, our observable universe is just one bubble among countless others, all separated by ever-expanding space and time. The fabric of the cosmos itself continuously gives birth to new universes, each crystallizing into existence as inflation recedes locally. Yet, within this endless spawning of universes lies a critical consequence. Each universe can possess different fundamental properties. The conditions that define physics, the strengths of forces, the masses of fundamental particles, even the number of spatial dimensions, could vary dramatically from one universe to another. Physicists have speculated about the nature of these alternative universes, and their conclusions are stark. The overwhelming majority would be dead, sterile, and devoid of complexity. If the fundamental constants were even slightly altered, many universes would never form stars, planets, or the conditions necessary for life. However, within this vast landscape of barren worlds, there exist rare pockets of habitable universes, just like ours. This statistical perspective suggests that we should not be surprised by the apparent fine-tuning of our own cosmos. Rather than being the result of design, it is simply a consequence of the vastness of possibility. We find ourselves in one of the exceedingly rare universes that permit complexity, because that is the only kind of universe where conscious observers can exist. This is the essence of the anthropic principle. We observe a life-permitting universe because only in such a universe could observers arise to ask the question. In this view, our finely tuned universe is not unique. It is just one successful roll of an infinite set of cosmic dice. While eternal inflation provides one pathway to a Level 2 multiverse, it is not the only theoretical framework that suggests multiple universes. Another idea has its roots in an ancient concept, the cyclical nature of existence. In Hindu cosmology, the universe is described as eternal, undergoing endless cycles of creation, destruction, and rebirth. Interestingly, a similar idea has appeared in modern physics. Throughout the 20th century, cosmologists, including Einstein, entertained the notion that our universe might not be a one-time event, but part of an ongoing cycle. Within the equations of general relativity, certain solutions allow for a universe that repeatedly expands and contracts, a cosmic cycle with no absolute beginning or end. This vision of a cyclic universe was appealing. Rather than being born from an inexplicable singularity, the universe could be one iteration in an eternal sequence. Entropy, the measure of disorder in a system, is an unavoidable feature of thermodynamics. Every process in the universe increases entropy, gradually moving from order to disorder. Over immense timescales, energy degrades, and the cosmos inches toward thermodynamic equilibrium, a state of maximum entropy where no further work can be done. This poses a dilemma for a cyclical universe. If a new universe inherits the entropy of its predecessor, then with each cycle, disorder accumulates. Over infinite cycles, entropy would only increase, raising the question, how could a new universe emerge with the low entropy necessary for structure and life? If cycles have been occurring forever, why hasn't all order already been lost? This challenge led many physicists to abandon the idea of an eternally cycling cosmos in favor of a singular Big Bang. Yet, just as inflationary theory was refined in the face of early challenges, new variations of the cyclic model have emerged. Some propose that entropy resets under extreme conditions. Others suggest hidden dimensions that recycle energy in ways we do not yet fully understand. Whether through eternal inflation or an endless sequence of rebirths, modern cosmology increasingly points toward a reality far grander than the universe we observe. We exist within a cosmos that may be but one bubble in an infinite frothing sea, or one moment in an endless cosmic cycle. The deeper we look, the more the multiverse seems not just plausible, but inevitable. If there are indeed higher levels of reality beyond our own, then the story of the universe is still being written, playing out across landscapes we can scarcely begin to comprehend. And yet, we have only scratched the surface. The Level 2 multiverse is but one possibility, one rung on the ladder of deeper realities. As we continue climbing, the cosmos grows even stranger, more intricate, and more profoundly interconnected than we ever imagined. Recent Nobel laureate Roger Penrose introduced an intriguing cosmological framework known as conformal cyclic cosmology. According to his hypothesis, in the distant future of our universe, all matter will inevitably decay into radiation, leaving behind an empty, featureless cosmos. As the universe expands indefinitely, it will reach a state of such vastness and simplicity that its geometry becomes indistinguishable from the highly uniform conditions theorized at the Big Bang. This leads to a profound implication. The past and future are intrinsically connected, forming a perpetual cycle of cosmic death and rebirth. Penrose's perspective is not the only one to suggest a continuous generational process in the cosmos. In the 1980s, physicist Lee Smolin proposed a radically different mechanism for cosmic evolution, the idea that black holes might serve as the birthplaces of entirely new universes. Rather than emerging within the confines of our existing space-time, these offspring universes would manifest as wholly independent realms, each with its own set of physical laws. If true, then each stellar collapse leading to a black hole could signify the genesis of another cosmos, suggesting a reality where new universes are constantly emerging. Smolin extended his theory by incorporating a principle akin to Darwinian natural selection. He postulated that if the fundamental parameters governing each new universe could vary slightly, akin to genetic mutations, then only those that support star formation and black hole generation would persist. Universes that failed to produce such structures would fade into insignificance, effectively being evolutionary dead ends. Over countless generations, this natural selection process would favor universes with physical laws that optimize black hole formation, potentially leading to a multiverse teeming with star-filled, habitable realms. Although speculative, Smolin's hypothesis suggests that our own universe might be the result of such a selection process, finely tuned by an invisible evolutionary mechanism favoring complexity and structure. Another cyclic universe model has recently gained traction, echoing an ancient mythological metaphor, the phoenix. Just as the immortal bird perishes in flames only to rise anew from its ashes, physicists Paul Steinhardt and Neil Turok have proposed the ekpyrotic universe model, a fresh take on cyclic cosmology inspired by string theory. In their vision, our universe exists as a three-dimensional brain floating in a higher dimensional space. Periodically, these brains collide, releasing immense energy that births a new universe with low entropy, effectively resetting the cosmic cycle. Unlike previous cyclic models, the ekpyrotic scenario avoids the entropy problems that once undermined similar theories, suggesting that cosmic rebirth could be a natural and eternal process. Despite its elegance, the theory has yet to gain widespread acceptance, with many physicists remaining skeptical of the concept of higher dimensional brains. In the broader quest for a unified understanding of the cosmos, few names stand out as prominently as Edward Witten. Unlike many of his contemporaries, Witten's path to theoretical physics was unconventional. Initially drawn to history, linguistics, and even journalism, he ultimately found his calling in mathematics and fundamental physics, where his insights into the topology of space and time set him apart as a visionary thinker. In 1990, his pioneering work earned him the Fields Medal, an honor typically reserved for pure mathematicians. But Witten had his sights set on a grander ambition, the elusive theory of everything, a framework that could reconcile all fundamental forces into a single, coherent mathematical structure. The search for such a theory has been a long and arduous endeavor. While quantum mechanics successfully describes three of the four fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity remains an outlier, governed by Einstein's general theory of relativity. The discrepancy between quantum mechanics and relativity has perplexed physicists for decades, suggesting that an even deeper, more fundamental theory must exist. Early attempts to unify these forces, such as the Kaluza-Klein theory, sought to introduce additional spatial dimensions, but ultimately fell short. Even Einstein, alongside brilliant minds like Hermann Weyl and Arthur Eddington, devoted years to this pursuit without success. By the 1970s, an exciting new framework known as supergravity emerged, founded upon the mathematical principles of supersymmetry. This theory posited that every known particle had a yet undiscovered superpartner, electrons with selectrons, quarks with squarks. However, supergravity encountered significant theoretical hurdles, and as physicists delved deeper, inconsistencies began to surface. Despite initial promise, the theory eventually faded from favor. Yet great ideas in physics rarely vanish entirely. In 1984, Michael Green and John Schwartz rekindled hope with the advent of superstring theory. The fundamental premise was as radical as it was elegant. Rather than treating elementary particles as indivisible points, superstring theory envisioned them as tiny vibrating strings. The different vibrational modes of these strings corresponded to different particles, unifying them under a single framework. However, the mathematics of string theory required additional spatial dimensions beyond our observable 3. Early formulations suggested as many as 26 dimensions, though refinements eventually converged on a more feasible 11, echoing the earlier supergravity theories. To reconcile these extra dimensions with observable reality, physicists proposed a mechanism known as compactification, wherein the additional dimensions are curled up into minuscule, intricate structures called Calabi-Yau manifolds. Though invisible to us, these hidden dimensions were postulated to influence the properties of particles and forces in our universe. Once again, hope soared that a true theory of everything had been discovered. But once again, the reality was more complicated. Instead of a single, unique theory of everything, physicists found themselves facing not one but 5 competing versions of string theory. The dream of a singular unifying framework seemed to be slipping away, replaced by a bewildering landscape of mathematical possibilities. Then, in 1995, at the annual String Theory Conference at the University of California, Ed Witten introduced a transformative idea. What unfolded in the wake of his insights would redefine the field and reignite the hope of unification. Witten's vision offered a new perspective on the fragmented theories, weaving them into a cohesive framework known as M-theory. This bold proposition suggested that the various string theories were merely different aspects of a more fundamental, 11-dimensional reality. N-theory posited that beyond the vibrating strings lay extended objects known as brains, capable of existing across multiple dimensions. The implications were profound. If correct, N-theory could provide the long-sought unification of all fundamental forces, seamlessly integrating gravity with quantum mechanics. Though the full mathematical structure of N-theory remains elusive, its conceptual breakthroughs have reshaped modern physics, inspiring new research into the deep fabric of the cosmos. The journey toward a theory of everything is far from over. Whether through conformal cycles, black hole progeny, brain collisions, or vibrating strings, physicists continue to push the boundaries of human understanding, striving to decode the ultimate nature of reality itself. As history has shown, even the boldest theories may fall short, but each step brings us closer to the fundamental truth that lies at the heart of the cosmos. Perhaps the 5 different versions of string theory were not as distinct as they initially appeared. Perhaps, rather than separate competing theories, they were merely different perspectives of a single, unified framework. From this revelation, M-theory was conceived, igniting what is now known as the second superstring revolution. The meaning of the M in M-theory remains elusive. Some suggest it stands for mystery, others magic, but to many, it signifies membrane, reflecting how the one-dimensional strings of string theory extend into two-dimensional sheets, or brains, within the higher dimensional space. This conceptual leap helps to resolve some of the mathematical challenges of string theory, though it does not eliminate them entirely. In reality, M-theory is not yet a fully developed theory, but rather a framework, a guiding vision toward which physicists strive. It has, however, brought one crucial realization into focus. Originally, physicists hoped that the elusive theory of everything would be singular and unique, an elegant mathematical structure dictating the exact parameters of our universe, such as the mass of the electron or the strength of gravity. However, that hope was irrevocably altered with the advent of N-theory. N-theory suggests that the earliest moments of the universe were marked by extreme temperatures and simplicity. As the universe expanded and cooled, the fundamental physical laws did not emerge as a predetermined inevitability, but rather crystallized out in a process akin to symmetry breaking. Crucially, this crystallization was not unique. There exist countless possible ways in which the fundamental parameters of physics could have solidified. This idea introduced what is now known as the string theory landscape. The sheer number of possible configurations remains an open question, but estimates suggest an astronomical figure, perhaps as many as 10 to the power of 500 possible universes, each governed by a distinct set of physical laws. Some physicists argue that this multitude of possibilities is not merely theoretical, but reflects an actual, physical multiverse. In this picture, the multidimensional realm of N-theory, referred to as the bulk, contains an uncountable number of universes, each residing on its own membrane, or brain. Each of these universes, through its unique crystallization of physical laws, occupies a different region within the vast string theory landscape. The implications of this are profound. Just as the theory of eternal inflation suggests an ever-growing multitude of bubble universes, N-theory posits a vast, possibly infinite collection of brain universes, each differing in its fundamental physics. However, this vastness brings a sobering realization. The overwhelming majority of possible universes within the landscape would be sterile and lifeless, with physical laws so hostile to complexity that no structure, let alone life, could ever emerge. If M-theory's multiverse exists, then much like eternal inflation's cosmic lottery, the overwhelming expanse of reality would resemble a cosmic graveyard, where habitable universes are rare exceptions rather than the rule. And yet, improbability is not impossibility. Among the many lifeless universes, a few would possess just the right conditions to harbor stars, planets, and even life. In such a reality, our own existence is not a consequence of fine-tuning, but of statistical inevitability. We exist simply because we reside in one of the exceedingly rare universes where conditions allow for observers to emerge. Of course, N-theory remains speculative. The string theory landscape is a hypothesis, and the idea that universes exist as brains in the bulk is far from proven. But for many physicists, the internal coherence of N-theory and its deep mathematical structure make it an appealing and promising direction for future research. Whether it ultimately proves to be correct or not, the pursuit of N-theory continues to inspire new approaches to understanding the fundamental nature of reality. As our understanding of the cosmos expands, the possibility of multiple, coexisting level 2 multiverses emerges, some envisioned as infinite inflating bubbles, others as cyclic phoenix-like rebirths, and yet others as brains adrift in the higher dimensional bulk. The once impenetrable fog of ignorance is receding, revealing a complex and layered multiversal structure. But is this the final revelation? Is this the furthest extent of cosmic strangeness? Level 3. What if I told you that you are immortal, that you will live forever? What if I could guarantee that no matter what obstacles you face, you would ultimately emerge victorious? What if I asserted, with absolute certainty, that you would conquer illness and even death? That even with a gun pointed at your head, survival could still be ensured? Such claims might seem absurd, the ramblings of a madman. But we have now arrived at the level 3 multiverse, where immortality is not just a possibility, it is inevitable. To understand how, we must begin with a deceptively simple question that has reshaped our understanding of reality. What is the fundamental nature of light? By the 1800s, scientists had debated for over a century whether light was a wave or a particle. The decisive experiment that seemed to resolve this question was conducted in 1801 by Thomas Young, a polymath often referred to as the last man to know everything. His contributions spanned multiple disciplines, from medicine to linguistics. Indeed, he played a crucial role in deciphering the Rosetta Stone. But for our purposes, his most significant work lies in the realm of physics. Young devised an experiment that was, in its setup, strikingly simple yet profound in its implications. A source of light was directed at a screen, with an intermediate barrier containing 2 narrow slits. If light were composed of particles, individual particles should pass through one slit or the other, producing 2 bright spots on the screen behind. But if light were a wave, it would diffract through both slits, creating an intricate pattern of interference, alternating bands of brightness and darkness. Young performed the experiment, meticulously shielding it from external light. He directed sunlight through a small aperture to act as a coherent source, and when he observed the screen, he saw an unmistakable interference pattern, compelling evidence that light behaved as a wave. For over a century, this view remained unchallenged. But as has so often been the case in physics, quantum mechanics arrived to disrupt our understanding. Quantum mechanics revealed that nature is not continuous, but quantized, chopped into discrete units. This extended to light itself. Albert Einstein, in a groundbreaking insight, proposed that light was made of discrete packets, now known as photons. But this posed a fundamental problem. If light was composed of particles, how could Young's interference patterns still emerge? This duality, in which light exhibits both particle-like and wave-like behavior, remains one of the great enigmas of physics. The key to understanding it lies in the language of quantum mechanics. Classically, objects have well-defined properties. A stone is here, it moves at this speed, and its future position can be determined with certainty. But in quantum mechanics, this certainty dissolves. Instead of a definite position and velocity, an electron is described by a wave function, an abstract mathematical entity that encodes all possible outcomes of measurement, but does not specify a single, definite reality. The wave function is spread across space, encompassing all possible states. In 1926, Owen Schrödinger derived an equation that describes how wave functions evolve over time. Using this equation, we can predict how light, or any quantum particle, interacts with Young slits. Because wave functions behave as waves, they interfere with each other, producing the very same interference pattern observed in Young's experiment. Problem solved? Not quite. If we repeat Young's experiment today with modern detectors capable of registering individual photons, an astonishing fact emerges. Each photon is detected as a discrete particle on the screen. The light travels as a wave, passing through both slits simultaneously, yet when it interacts with the detector, it manifests as a particle, appearing at a single point. This is not just true for photons, it applies to all quantum particles. And herein lies the crux of the issue. How does a smeared-out wave function suddenly collapse into a discrete particle? It was two of the towering figures of quantum mechanics, Niels Bohr and Werner Heisenberg, who first proposed an answer. Their approach, known as the Copenhagen interpretation, introduced an extraordinary concept. The observer plays a crucial role in determining reality. In this view, the wave function represents a probability distribution as first proposed by Max Born in 1926. The probability amplitude tells us where a particle is most likely to be found. But for this wave function to translate into the detection of a single photon or electron, it must collapse into a single outcome. When a particle is fired at the screen, its wave function fans out, passing through both slits. The wave function interferes with itself on the way to the screen, but upon measurement, it collapses into a single, localized particle. We cannot predict precisely where each photon will appear, only the statistical likelihood of different outcomes. While the Copenhagen interpretation has been confirmed through countless experiments, it has an unsettling feature. Nowhere in the mathematics of quantum mechanics is there a mechanism for wave function collapse. It must be added as an ad hoc rule, an unsatisfactory patch on an otherwise elegant framework. This unresolved issue, known as the measurement problem, remains one of the great mysteries of physics. Some have proposed that the very act of detection collapses the wave function. John von Neumann went further, suggesting that consciousness itself plays a role, that an observer's awareness is essential to defining reality. This radical idea raises bizarre implications. If consciousness is required to collapse wave functions, does that mean no quantum measurements occurred before the first conscious beings emerged? Could the early universe have existed in a superposition of states until intelligent life arose to observe it? Despite its popularity in quantum mechanics courses, the Copenhagen interpretation remains deeply controversial. Many physicists are uneasy about its reliance on an arbitrary collapse mechanism. Cosmologist Sean Carroll has described the notion of wave function collapse as an embarrassment to physics. Thus, alternative interpretations have been proposed, some of which lead directly to our Level 3 multiverse. The most controversial of these alternatives is the many worlds interpretation. In 1942, a 12-year-old Hugh Everett III wrote to Albert Einstein, asking whether the universe was governed by chance or by some deeper unifying principle. 12 years later, during a late-night discussion over the bizarre implications of quantum mechanics, Everett formulated what would become his most profound contribution to theoretical physics. His goal was simple: follow the mathematics of quantum mechanics to its logical conclusion, no matter how strange the implications might be. And with that, he sought to confront the measurement problem head-on. Indeed, the Copenhagen interpretation relied on the so-called Heisenberg cut, an arbitrary distinction between the microscopic quantum world and the macroscopic classical world, designed to keep the more perplexing features of quantum mechanics at bay. Hugh Everett III rejected this distinction outright. He dismissed the notion of wave function collapse entirely and proposed a radical alternative. To understand his reasoning, let us consider an experiment in a controlled laboratory setting. Traditionally, the experimenter is seen as separate from their apparatus, influencing the experiment by altering variables such as temperature or magnetic field while remaining an external observer. However, Everett realized that this distinction is fundamentally flawed. Everything in the laboratory, including the experiment itself, is composed of electrons and atomic nuclei, each described by its own wave function. Consequently, the experiment is not a single definite entity, but rather a superposition of all possible wave functions. And crucially, so is the experimenter. A complete quantum mechanical description of the laboratory must include the superposition of both experiment and observer. The entire system, the laboratory, the apparatus, the experimenter, is a superposition of all possible states. But if the observer and the experiment are entangled in this superposition, where does wave function collapse occur? Everett's realization was profound. The problem only deepens when we consider the entire universe. The universe itself is not an isolated system. It is the totality of existence. The universal wave function, therefore, must encode all the particles and interactions within it, including those that make up you. In Everett's formulation, the Schrödinger equation dictates how this universal wave function evolves over time, encompassing all possible futures. But if the universe follows a deterministic evolution via the Schrödinger equation, where does the randomness of quantum mechanics originate? Everett's answer was groundbreaking. The universal wave function does not merely encode our observed reality, it encodes all possible realities simultaneously. In this formulation, every quantum event is not singular, but rather the branching point of parallel realities. The act of measuring an electron in a superposition of two states does not cause the wave function to collapse. Instead, the coherence between nearby universes is broken, and these universes decohere from one another. In some universes, the electron is found in state A. In others, it is found in state B. Since you, the observer, are also part of the universal wave function, there exist versions of you that observe state A and others that observe state B. In that moment, the universe is split, forming two distinct branches. And this happens at every quantum measurement, at every quantum interaction. Every probabilistic outcome is realized in some branch of the universal wave function. Individual universes with divergent histories crystallize out of the ultimate superposition. In the many worlds interpretation, these other universes are just as real as our own. In some, an alternate version of you exists, differing in subtle or drastic ways. In others, you never existed at all. The result is an infinite web of realities, each branching at every quantum event. At first glance, this may seem analogous to the level 1 multiverse, where vast parallel worlds unfold. However, the level 3 multiverse proposed by Everett is far deeper. Here, every branching universe can contain its own level 1 multiverse or even level 2 structures, nested infinities beyond comprehension. From the simple observations of Young's double-slit experiment, we arrive at a breathtaking conclusion. The many worlds interpretation gives rise to an endless sea of parallel universes. Naturally, such a radical idea has faced resistance. Some physicists dismiss many worlds as excessive, arguing that it postulates an unfathomable number of universes simply because physicists could not determine which version of reality was real. Nobel laureate Gerard T. Hooft famously remarked, "It would be a stupendous number of parallel worlds, which are only there because physicists couldn't decide which of them is real." Everett's insights were largely ignored during his lifetime. His thesis was met with indifference or outright dismissal, even by Niels Bohr himself. Disillusioned, Everett left academia after completing his PhD, working instead as a computer scientist. He died in 1981, never witnessing the resurgence of interest in his ideas. However, a new generation of physicists has embraced many worlds, recognizing it as one of the most consistent and elegant interpretations of quantum mechanics. To many, it is the only interpretation that follows quantum mechanics to its logical conclusion without invoking ad hoc collapse mechanisms. Yet, profound questions remain, chief among them, consciousness. What happens to the conscious self as universes diverge? Do distinct copies of an individual emerge in each branch, each retaining all prior memories? If so, what defines the continuity of identity across multiple realities? This is the domain where physicists and philosophers collide. Consider a thought experiment. A coin is flipped, and if it lands on tails, you are executed. If it lands on heads, you survive. Each time you flip the coin, you know that the probability of survival is 50%. If the Copenhagen interpretation holds, eventually you will lose this game. But in the many worlds framework, at the moment of each toss, the universe branches. In one reality, the coin lands on heads and you survive. In another, it lands on tails and you perish. With each subsequent flip, the multiverse continues to split. Yet, in at least one universe, there will always be a version of you that experiences a continuous sequence of lucky outcomes, an immortal observer navigating an improbable but real sequence of events. Does this mean that in the many worlds interpretation, you will always find yourself on the lucky path? Is consciousness bound to the thread of survival? These questions lie at the edge of scientific inquiry, blurring the lines between physics and metaphysics. It seems that we have reached the furthest limits of our exploration of multiversal theories. What could be beyond an infinite superposition of all possible universes? To answer that question, we must relinquish even our deepest assumptions about reality itself. For in the Level 4 multiverse, we will confront the idea that the cosmos is not merely a physical entity. It may be nothing more than a mathematical structure, a dream woven from pure abstraction. Level 4. What is reality? At first glance, the answer seems self-evident. We are surrounded by tangible matter, solids, liquids, and gases. Yet, as we have seen time and again, our intuitive perception of reality is deceptive. If we probe deeper, all matter is composed of atoms, which in turn consist of subatomic particles such as electrons and quarks. But even these so-called fundamental particles do not provide the ultimate foundation of reality, for their interactions are governed by mathematical laws, expressed through equations that define the fundamental forces and the structure of the cosmos itself. This leads to an unsettling question: where do these mathematical laws exist? If reality is dictated by numbers and equations, then where is the framework that encodes these rules? It is here that we arrive at Max Tegmark's Level 4 multiverse, a radical yet logically consistent proposition. This multiverse is not composed of space, time, or matter, but of pure mathematics. Every conceivable mathematical structure exists as a universe in its own right, forming an infinite ensemble of realities. Within this framework, all possible multiverses, from the quantum branches of many worlds to the inflating bubbles of Level 2, are simply different manifestations of mathematical objects. The implications of this idea are profound. In many ways, the Level 4 multiverse resembles the controversial simulation hypothesis, the notion that our reality is nothing more than an advanced computation executed on a cosmic supercomputer controlled by entities beyond our comprehension. However, in Tegmark's vision, there is no need for a physical machine. The mathematical structures themselves are the fundamental substrate of existence. Reality, in its purest form, is simply a self-contained mathematical construct. At this point, we are navigating the farthest edges of speculation, where theoretical physics blends into the philosophical. We began our journey by peering beyond the cosmic horizon, asking whether other universes might lie beyond our own. Now, we find ourselves questioning the very nature of existence itself. One thing is clear: the multiverse is not a single, well-defined concept, but rather an intricate web of ideas. Some are deeply rooted in established physics, while others drift perilously close to the realm of science fiction. Before we conclude our exploration, a word of caution is warranted. In public discourse, discussions of the multiverse often provoke fierce debate. Some physicists view it as an inevitable consequence of our best theories, arguing that eternal inflation, for instance, leads inescapably to a vast ensemble of universes. Others champion N-theory and the string theory landscape as the natural explanation for our universe's finely tuned parameters. Even relatively straightforward considerations, such as the nature of dark energy and the structure of the cosmic horizon, seem to point toward a multiversal framework. Yet, there are staunch opponents who reject the multiverse outright. To them, discussing unobservable universes is fundamentally unscientific. They argue that science requires empirical verification, falsifiable predictions that can be tested through observation or experiment. If parallel universes are forever beyond the reach of our instruments, they should be relegated to the realm of metaphysics rather than physics. However, neither side holds absolute authority. The truth is that multiverse theories remain in their infancy. While some theoretical foundations have been established, they are far from complete. Many key questions remain unresolved. How precisely did universes crystallize out of eternal inflation? Can string theory, despite its mathematical elegance, ever be experimentally verified? Does the many-world interpretation of quantum mechanics truly reflect physical reality, or is it merely a convenient abstraction? And can the Level 4 multiverse ever be anything more than an intriguing mathematical conjecture? Despite these uncertainties, the possibility of testing multiversal ideas should not be dismissed outright. Advances in observational cosmology may one day uncover indirect signatures of parallel universes. Some researchers propose that scars in the cosmic microwave background might reveal evidence of past cosmic collisions, remnants of interactions between our universe and others in the higher dimensional bulk of N-theory. The geometry of the universe itself, if found to be perfectly flat and infinite, might lend further weight to the idea of an endless cosmic expanse. For now, however, direct evidence of other universes remains elusive. The search for parallel worlds is still in its infancy, and we cannot predict how our theories will evolve in the coming decades. It is entirely possible that the multiverse will forever remain hidden within the fog of the unknown, an idea tantalizingly out of reach, yet eternally fascinating in its implications. And so, we stand at the boundary of knowledge, gazing into the abyss of possibilities. Whether the multiverse will ever be revealed, or whether it will remain an enigma woven into the fabric of theoretical physics, is a question only time and relentless scientific inquiry can answer.